Hello, everyone, and welcome to the OneClass channel. My name is Donna, and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or tutoring, then check out the links in the description below. So now let's just get started on our set of questions for today's session. Okay, so question 1 just asks, what is KSP? Okay, so let me just write over here that KSP is the solubility product constant. So the solubility product constant is the equilibrium constant for a solid substance dissolving in an aqueous solution. So in other words, it is also the level at which a solute dissolves in solution. Okay, so let me just write out a general chemical reaction involving a solid, let's call it compound or element A. And when it dissolves, it forms B plus C. So if we imagine this as a balanced chemical reaction, we can say that the smaller lowercase letters would be the coefficients that are placed in front of the elements to make it a balanced chemical equation. So from here, we can write a KSP expression. And typically, it's the concentration of your products to the power of their coefficients divided by the concentration of your reactants to the power of your coefficients. But in this case, element A is a solid, so it won't be a part of the expression. And I'll just write that note down here that the solids are not included. And this is because their concentrations do not change the expression. Okay, so let me just finish off writing the KSP expression. It'll be the concentration of B to the power of its coefficient multiplied by the concentration of C to the power of its coefficient. And this would be the KSP expression for this general chemical reaction. Okay, so let's see what the junior tutor said. KSP, or the solubility product constant, represents the product of ions at equilibrium. It dictates the amount of solute that can be dissolved in the aqueous solution. A higher KSP means a more soluble substance. The general dissolution reaction can be represented by the chemical reaction below, where A, solid, makes C aqueous plus D aqueous. At equilibrium, the KSP can be calculated by multiplying the concentrations of the products. Each product is also raised to its coefficient. Yep, so this solution is correct. Okay, so question 2 is a multi-step question. It says to determine the balanced chemical equation for this reaction. C8H18 plus oxygen makes carbon dioxide plus water. Part A, enter the coefficients for each compound in order separated by commas. So I'll just show the balanced chemical equation. Part B, 0.280 moles of octane is allowed to react with 0.63 moles of oxygen, which is the limiting reactant. Part C, how many moles of water are produced in this reaction? And then part D, after the reaction, how much octane is left? Okay, so let's start off trying to balance. We have octane, gas, plus oxygen gas makes carbon dioxide plus water. Okay, so this is an example of a combustion reaction. And the reason that we know this is because combustion reactions always have like a hydrocarbon. In our case, it's the octane, and it reacts with oxygen to form carbon dioxide and water. So it will always react with oxygen, and the products will also be CO2 plus H2O. So that's how we know we have a combustion reaction. Okay, so now we want to balance this equation. So there's a method that I like to use when balancing combustion reactions. And the first one is just to balance my carbons. So when we want to balance out the carbons, you'll see that the hydrocarbon, which is octane, contains 8 carbons. So I need to write an 8 in front of CO2 so that my carbons are balanced. And then after I balanced out my carbons, next I want to balance out my hydrogens. Okay, so on the left side we have 8 hydrogens, and on the right side we have 9. We have 2, but we need to put a 9 in front so that both sides have 18. And then lastly, all my carbons and hydrogens are balanced, and now I want to balance out my oxygens. So the reason I do this last is because when I balance out my carbons, this affects the number of oxygens. And similarly, when I balance out my hydrogens, this also affects how many oxygens as well. So now that I know how many oxygens are on my product side, which is 16 plus 9, so we have 25 oxygens. On the product side, I'm going to put a 25 in front of O2 and then divide it by 2 to get in total 25 oxygens. Okay, so we're not quite done yet. Sometimes it might be easier to not read this balanced equation having a fraction. So to get rid of the fraction, I'm just going to multiply this whole thing by 2. And then I'm going to write my new balanced equation just below right here. So now we have 2 moles of octane plus 25 O2 makes 16 CO2 plus 18 H2O. Okay, so now everything should be balanced. And we can move on to part B. So part B is asking which one is the limiting reactant. Is it octane or oxygen? Okay, so the limiting reactant, I'll just write a quick definition of what it is. Basically, it's one of the reactants that runs out first. Because most of the time you won't have an equal amount of reactants, and they won't always just, when one runs out, the other one runs out. Like usually you have one that has more. So the one that runs out first is our limiting reactant. So there are different methods that people like to do to try to find out which one of their reactants is limiting. One way that I like to do is that I like to find how much product is formed if the reactant went to full completion. So basically I try to find the number of moles of one of my products, and the one that has the less amount is the limiting reactant. So let's start off with the octane first. So we have 0.280 moles of octane. And now I'm going to multiply this value by the mole ratios in order to find out the number of moles of water that is produced. So if we multiply, you'll notice that because of our balanced equation, we can see that there are 18 moles of water that is produced with every 2 moles of octane. That's why it's important to make sure that your reaction is balanced, because we can do the molar ratios and find out how much of our product we can actually form. Okay, so if we multiply 0.28 by the ratio 18 over 2, you should get 2.52 moles of H2O produced. Okay, so this is with octane. And now we're going to see how much 0.630 moles of oxygen will form however much water. Okay, so let's just multiply by the molar ratio of water and oxygen. So again, 18 moles of water will be produced, and the coefficient for oxygen is 25. And if we do this calculation, then you'll notice that only 0.454 moles of H2O is produced. And since it is less than how much the octane produced, then we can say that oxygen is our limiting reagent. Okay, so part C asks how many moles of water are produced in the reaction. And since the oxygen will run out first, then the reaction can't produce any more water since all the oxygen is gone. So therefore, we only produced however much the limiting reagent produced before it runs out. And we already calculated this to be 0.454 moles of H2O. So then we can just move on to part D. After the reaction, how much octane is left? So basically, we have to find the unreacted moles. So to do this, it is just your starting moles. So basically, we're trying to find out how much octane was left over if all of it reacted with the limiting oxygen. So we started off with 0.28 moles of octane. We're going to subtract how many moles reacted. So to do this, we need to multiply by the molar ratio between the limiting reactant, which is oxygen, and the octane. Okay, so it's going to be multiplied by 2 moles over 25. And then this will give us the unreacted moles. Okay, so let me just calculate this. Should get around 0.26 moles left over. Okay, so let's see what the junior tutor said. For part A, we can balance this equation by inspection, starting with carbon, then either hydrogen or oxygen, whichever is simpler. Okay, so you can see that they also got 2 moles of octane plus 25 oxygen makes 16 carbon dioxide plus 18 H2O. B, the limiting reactant, is the reactant that limits the amount of products formed. The limiting reactant is the reactant that gives the smaller amount of product. For octane, we have 2.52 moles of hydrogen produced, or water produced. And then for oxygen, they have 0.4536 moles. Therefore, the limiting reactant is oxygen. We have computed this in B. Yep. And then to answer this, we calculate for the moles of octane using the moles of H2O produced. Then we subtract the obtained amount of mole from the initial moles of octane. Okay, so they found the moles of octane that reacted by multiplying it by the molar ratio of octane and water. So this is a different method of doing that. And they got 0.0504. And for their unreacted octane, they got around 0.2296. Yep, so that's another way of doing it. I'm just going to say this solution is correct. Okay, so now let's move on to question 3. Calculate the standard entropy change for the following reaction at 25 degrees Celsius. So we have H2O gas reacting with carbon, making hydrogen gas, plus carbon monoxide. Okay, so the first part of answering the question is just to look up the standard entropy of formation of both reactants and products. Let me just write down everything we need to find. We need to find the delta S of formation of H2O gas. Delta S of formation of carbon solid. Delta S of formation of hydrogen gas. Let me just write these on the other side. Okay, so these standard entropy of formations, the values are given in a table. So usually it might be given in the question, or you have to look it up in a textbook. But I will just look it up on Google. Standard entropy of formation table. And then you'll see that most of them are all given. Okay, so let's just find one that has everything that we're looking for. I think that's missing some. Yeah, so depending on which table that you use, they might have slightly different values. Okay, so let's just use this one. So H2O gas, its standard entropy of formation is around 188.8. And the units are joules over mole times Kelvin. For carbon solid, this can also be carbon graphite. So it's the very first one in the column, around 5.74 joules over mole times Kelvin. Hydrogen gas, 130.68 joules over mole times Kelvin. And then carbon monoxide, it's right here. So 197.67 joules over mole times Kelvin. Okay, so after we looked it up, we can use the following equation to calculate the standard entropy change for the whole reaction. So let me just write out the expression for that. Delta S of the reaction is equal to the sum of our products minus the sum of the delta S of formation of our reactants. Okay, so depending on how many moles of each compound this will affect our final delta S value. But if we look at our balanced equation, you'll notice that everything is 1 to 1 to 1 to 1. So that should be pretty easy to do. And now we just have to plug in all the values that we found in the previous step. So starting with the products, we have 1 mole of H2, and then this is going to be multiplied by 130.68 plus 1 mole of carbon monoxide multiplied by 197.67, and then that whole thing, we need to subtract all our reactants. 1 mole of H2O times 188.8, and then lastly 1 mole of carbon multiplied by 5.74 joules over mole times Kelvin. Okay, so now that we have that all written down, you'll notice that the moles will cancel out. And then we're left with our standard entropy change, which is 133.86, and the units will just be joules over Kelvin. Okay, so let's see what the junior tutor said. So I think they may have gotten their units Yeah, so their units are just in kilojoules. Maybe they read the chart wrong, but they got the same value, except it just should be joules over Kelvin. But their explanation says the entropy change in a chemical reaction is given by the sum of the entropies of the products minus the sum of the entropies of the reactants. As with other calculations related to balanced equations, the coefficients of each component must be taken into account in the entropy calculation. Formula is delta S of reaction is equal to the sum of the N times the delta S of formation of the products minus the sum of the N times the delta S of the reactants. Using any tables or references, the standard entropy of formation of the reactants and the products must be determined. In the problem, we are given H2O plus carbon makes H2 plus CO. Yep, so here they just have their units in kilojoules per mole over Kelvin. So let me just check another table to see what units they use. Yeah, so typically it is joules. Let me check another source, just in case. This is delta G. Yeah, but for the delta S values, they're usually in joules. Yep, so even here, the delta S for H2O gas is 188.8 joules over mole times Kelvin. So I think it's just a minor mistake that they made. But basically, they have the same math showing that everything was a 1-to-1 ratio, and they got 133.8. Okay, so the Explanation was correct. Explanation and calculations are correct. However, the units should be joule over Kelvin instead of kilojoule over Kelvin. I'll say this is incorrect. Okay, so moving on to question number 4. What are the strong 7 acids? Okay, so I'll just write all the strong acids. We have hydrochloric acid, hydrobromic acid, hydroiodic acid, and then we move on to our polyatomic ions. So we have sulfuric acid, nitric acid, fluoric acid, and perchloric acid. So all the strong acids means that they dissociate completely into its ions. Okay, so let's say we had a solution of HCl. It will dissociate into its ions in water 100%. Okay, so let's see what the junior tutor said. There are a total of 7 strong acids in the field of chemistry. They are hydrochloric acid, HCl, hydrobromic acid, HBr, hydroiodic acid or hydriodic acid, denoted by Hi, sulfuric acid, H2SO4, nitric acids, HNO3, fluoric acid, HClO3, and perchloric acid, HClO4. These acids completely dissociate in water into their constituent ions, hence the term strong acids. So this solution is correct. Okay, so question 5. Determine whether CHCl3 is polar or nonpolar. Okay, so let's write down the chemical structure of CHCl3. Okay, so if we call the electronegativity values of a chlorine atom versus carbon and hydrogen, you'll remember that chlorine is more electronegative. So because of this, all of these chlorine atoms will create dipole moments in the direction of the chlorines. So we can say that CHCl3 is polar. And this is because both the hydrogen and, well, I guess just the hydrogen. So the hydrogen will not cancel out. The 3 electronegative chlorine atoms. Okay, so you can see that there is an unbalanced sharing of electrons. So we can show that this molecule has partially negative sides and then a partially positive side where the hydrogen is. So this creates a non-zero dipole moment, making this molecule polar. Okay, so let's see what the junior tutor said. The given compound consists of carbon, hydrogen, and chlorine atoms. The electronegativity of carbon is 2.5, the electronegativity of hydrogen is 2.1, and the electronegativity of chlorine is 3.0. The difference between the electronegativity of carbon and hydrogen is 0.4, hence the bond between them is nonpolar. Difference between the electronegativity of carbon and chlorine is 0.5, hence the bond between them is polar covalent. Given these, the structure is as follows. Since the 3 polar bonds are not symmetrical, they do not cancel each other, hence there's a net dipole, and we can say that CHCl3 is a polar compound. So this solution is correct. Okay, so question number 6 is kind of like similar to the previous question, except it asks, explain why CHCl3 is polar, why CCl4 is not. So I can just write this on the same page just so that we compare. And now let me draw my structure for CCl4. Okay, again, chlorine is more electronegative than the carbon. So we'll see all of the dipole moments that are created by these electronegative chlorines. But this time, the molecule is symmetrical, and all of the chlorines will cancel each other out, and CHCl3, which is shown above it, we have a hydrogen, which isn't as electronegative as all the other chlorines, so it won't be able to cancel out, showing that there's a side that's partially positive and a side that is partially negative. But here, they all cancel out. So I can say CCl4 is nonpolar, I'll say CCl4 is a nonpolar molecule. So the reason I reworded it and said that it's a nonpolar molecule is because the chlorine-carbon bond itself is a polar bond, but the molecule as a whole is nonpolar. So don't get confused by that termination. So this is a nonpolar molecule since it's symmetrical. And the chlorine atoms will cancel each other out. So we have no dipole moment. Okay, so let's see what the junior tutor said. Polarity is affected when there is a net dipole moment in the molecule. So since both compounds have a polar carbon-chlorine bond and the same tetrahedral geometry, what we must consider is whether the dipole moments cancel each other out. Consider the structure shown below. Yep. When we apply the dipole moments to the structures, we get figure 2. The dipole moment in red and the net dipole moment in blue of CHCl3 and CCCl4. As seen in figure 2, the dipole moments of the carbon tetrachlorine cancel each other out. This means that it will not have a net dipole moment and will not be polar. On the other hand, CHCl3 has a net dipole movement going down, so it shows it going downwards from the molecule, so this molecule will be polar. Yep, so that's exactly why. So this solution is correct. Okay, so that was 5 and 6. So question 7. How many quarts are equal to a gallon? There are 4 quarts in 1 gallon. And we can remember this because if you look at the word quart, it's kind of similar to quarter. Which is 1 over 4. That's another way you can remember it as well. So let's see what the junior tutor said. A quart is equal to 1/4 of a gallon, hence the name quart. Converting 1 gallon to quarts, we'll have 1 gallon times 1 quart over 1/4 gallon is equal to 4 quarts. Note that for the conversion factor, the desired unit, which is the quart, is placed in the numerator, and the unit to be cancelled, which is gallon, is placed in the denominator. Hence, there are 4 quarts in a gallon. Yep, so this solution is correct. Okay, so question 8. Given below is the reaction of 2-chlorobutane. And then it shows it reacting to form products A and B. So part A says, what are the products A and B? Part B, how would the reaction proceed? Draw the reaction mechanism. Okay, so let's draw out the mechanism first, and then that will help us answer part A. So I'll just do it all in one go. Starting with our 2-chlorobutane. It is reacted with this sodium iodide. Okay, so sodium iodide is ionic. So I'll just show the charges that sodium is positive and the iodine is negative. So this will attack the carbon that contains the chlorine, and we'll kick it off. Forming product A. Which is 2-iodobutane. Okay, so let me just write what happens first. So this is product A. So what happened is an SN2 reaction. So SN2 occurs. And this is since the negatively charged iodine is a strong nucleophile. Okay, so that's how we got product A. And then this reacts with Na plus the sulfur is negatively charged, attached with a methyl group. So similarly, this will attack the carbon containing the iodine, kicking it off. And we're left with a sulfur methyl group. Okay, so this is product B. And then we can say that another SN2 reaction occurs. Okay, so let's see what the junior tutor said. The reaction shows 2-chlorobutane, an alkyl halide, reacting to sodium iodide. The most likely reaction to happen here would be a nucleophilic substitution. Nucleophilic substitution has two types. To know which type of nucleophilic substitution would occur, we need to look at the substrate, 2-chlorobutane, and the nucleophile. First, the substrate is relatively free. That is, the partially positive carbon, C2, is a 2-degree carbon that would allow for it to react either through SN1 or SN2. To differentiate, we need to now look at the nucleophile. The nucleophile is the iodide ion, I-. Ions are strong nucleophiles, so this reaction would occur via SN2. Knowing this, the first product is 2-iodobutane. Notice that the wedged line became a dashed line after the reaction. This is a result of the inversion that is a characteristic in SN2 reactions. And the question is a multi-step reaction, so we must react 2-iodobutane with the NaSCH3. Again, we look at the nucleophile. This is also an ion, and thus will react with 2-iodobutane via SN2. The product would be, so then it would show how it is now a dashed bond as well. The resulting product, butyl methyl sulfide, is inverted as well, since the reaction is via SN2. Thus, filling the blanks in the reaction gives us A. And then B, with that, we can make the reaction mechanism, which will be as follows. So they showed the iodine ion coming in and attacking it from the opposite side, forcing the chlorine to act as a leaving group. And now we have the product A. And then secondly, another SN2 reaction occurs. And then there's an inversion of the product. And they have the same product as I do. So this solution is correct. Okay, so on to question number 9, which I think is the last question we have time for. What are intermolecular forces present in water? So let's draw a molecule of water, which is H2O. Okay, so oxygen is more electronegative than hydrogen. So I can show a dipole moment being formed in the direction of oxygen. So because of this, one side of water will be partially negative, and then the other side will be partially positive. So because of this, one water molecule can attract another water molecule that is also partially positive and partially negative. So here I can show that this oxygen is partially negative. These water molecules are partially positive. And then this attraction of the partially positive side of one molecule with a partially negative side of another molecule is called hydrogen bonding. Okay, so this is an example of one of the intermolecular forces present in water. And in general, we can also call it a dipole-dipole reaction. And another intermolecular force that's present in water is something called London dispersion. So this is when electrons in two adjacent atoms occupy positions that make atoms form temporary dipoles. So it's a very weak interaction, but it is present in most substances. Okay, so these are the three main intermolecular forces present in water. And the junior tutor said, to answer this question, we need to review first the concept of intermolecular forces. Intermolecular forces are forces that hold molecules together in liquid or solid. In general, intermolecular forces are much weaker than intramolecular forces such as covalent bonds. Intermolecular forces play an important role in the melting points of solids and boiling points of liquids. The liquid boils when the molecules have gained enough energy to break the intermolecular attractive forces. In the same manner, solids melt when the molecule has enough energy to overcome the intermolecular attractive forces that hold the molecules together. There are three types of intermolecular forces. These are dipole-dipole interactions, London dispersion forces, and hydrogen bonding. The water molecule is consisted of two hydrogen atoms bonded to an oxygen atom. Its overall structure is bent due to the electronegativity difference in the oxygen atom, and also the lone pairs of oxygen. Oxygen atom forms hydrogen bonding, the H atom, and also carries two unshared electrons that caused the difference in electronegativity. Water is polar in nature. The bonds formed by the hydrogen atoms with oxygen are called hydrogen bonds. I'm just gonna make a note that it's because of the difference, the partially negative and partially positive sides of water, that it attracts another water molecule. Hydrogen bonds are weak interactions formed between, so here it is. So hydrogen bonds are weak interactions formed between hydrogen with a partially positive charge and a more electronegative atom, in this case oxygen. Hydrogen can also form hydrogen bonds with other electronegative atoms such as oxygen, nitrogen, or fluorine. Yep, so I'll just say this solution is correct. Okay, so those are all the questions we have for today. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. And if you enjoyed today's video, go ahead and give it a thumbs up and a comment. And also don't forget to share with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.